we'll start there. Yeah, Emily, we're on 3-4? Yeah. Is that correct? Okay. Why are you not working? Ugh, stupid machine. Try it again. Okay. Okay, and you said 45? Okay. Then get out of here. $45. So we're just looking to find the derivative. So, Emily, right here from jump, I would probably rewrite this to just kind of emphasize like my inner to outerness. So the outermost is cosine, and then the square root, and then sine, and then tangent, and then pi x. So there's a whole heap of layers through this. So we'll start for the first layer. So the derivative of cosine is negative sine. And then everything else is going to just kind of stay the same. And then I have times the derivative of the insides. And the derivative of a square root is like that. And then I have times the derivative of the inside. And then the derivative of sine of tan x, well, that's cosine tan pi x. Derivative of tangent pi x. And derivative of tangent is secant squared. Oops. And the derivative of pi x is just pi. So I'd have negative sine square root sine tan pi x times 1/2 sine tan pi x to the negative 1/2 times cosine of tan pi x times secant squared pi x times pi. So all that stuff just kind of gets stuck together. Does that feel okay on how I kind of stepped through the layers there to get to that? That's pretty nasty, right? What do you think? Now, like, could I simplify this a little bit and combine some terms here? Yeah, maybe, but like, I don't want to. I would be perfectly happy with this as my final answer. Emily, you okay?
Yeah.
You're just making some faces over there that don't look real happy.
You have to take the derivative of each piece separately, because I think what I did is I did the product rule of like.
Yeah, there's no multiplication going on. It's all composition. So again, like once you get super comfortable, you might be able to do that all in one step. I wouldn't have attempted it even with where I'm at. I'd have just been like, this is too many chains in a row. I'm going to screw this up if I don't like one chain at a time. Because if I look, that's 1, 2, 3, 4, 5 chain rules, it looks like that I used on that. So again, I just do the derivative of the outside times the insides. Oh, that's another chain rule. So like new outside, derivative new inside. Oh, another chain rule. And just kind of keep stepping one step at a time through. Paulo?
Why is it after that second section to the negative 1/2 power? Why is it negative?
Because I rewrote the square root as to the 1/2.
Yeah.
So when I took the derivative, the exponent comes to the front and I subtract 1. Elena.
Why did you multiply by sine?
So I did the derivative of the outside. The outside function here is like the square root. And then I have times the derivative of the inside. Right? So the inside is sine of tangent. Do you see what did I answer your question or no? Yes? Michael?
This question from 3.2, can we do number
31 from 3.2?
or 3.3?
3.3, sure. And you said 31?
Yep.
Yes, sir. Okay. So it says, find an equation of the tangent line to the given curve at the specified point. We're doing 31. So I know that the slope is going to be the derivative evaluated at 1, right? So to find the derivative, I'm going to be using the quotient rule. So that's the bottom times the derivative of the top minus the bottom, the bottom, nope, I meant times the top, jeepers creepers, times the derivative of the bottom, all over bottom squared. Oh, what did you ask for?
Is this from 3.3?
No, this is 3.2. Did you want 3.3?
Yeah.
Oh, that's my apologies. Never mind then, everybody. 3.3. And we're looking for number 31, which is like a story problem or something, right? Let's see.
Oh, yeah. No.
Okay. Thank you. Yeah, no problem. So it says use the quotient rule to differentiate the function. Yada, yada, yada. Okay. Well, that's good. We just said what the quotient rule was. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So far, so good? Okay. What's the derivative of tangent x minus 1? Secant squared, and really minus 0, but we don't need to say anything about the minus 0. Very good. And what's the derivative of secant? Secant x times tangent x. We're all over secant squared. Oops. So I'm going to just do a little reducee so I can do that right away. So my numerator then has secant squared x minus tangent squared x plus tangent x over secant x. So far, so good? Okay. Does this look familiar? That is a trig identity. So I know that most of us probably remember sine squared plus cosine squared is equal to 1. If I divide everything by cosine squareds, I'm going to get tangent squared plus 1 equals secant squared. And so if I subtract the tangent squared over, I see that secant squared minus tangent squared is just 1. Or you could have like looked that identity up. I think if you look at the front cover of your textbook, that's in there. And that's probably about as good as we can do. Maybe not. If I multiply the top and bottom by cosine, I'd get cosine x plus sine x over 1. Maybe that's better. But somewhere along the lines, you call any of those what the derivative is equal, depending on how much simplification you want to do. Part B says then simplify first before you find the derivative. Okay. So I had tangent x minus 1 over secant x. So I'm going to do that same simplification I just did there at the bottom. Cosine times tangent is sine. Oops. And sine or secant times cosine is just 1. So if I do the derivative now, well, that's easy. Derivative of sine is just cosine. And derivative of cosine is just negative sine. Woo! That was like an improvement. Avoid having to do the quotient rule and all that trig identity mumbo jumbo. Part C says show that your answers for A and B are equivalent. Well, I did that already. So I guess like this stuff is like C. Which way did you prefer?
Second.
Yeah, part B, right? Like, if you got triggies, maybe take a quick pass to see if, like, can I eliminate having to do a quotient rule or a product rule or something by just doing a little bit of, like simplifying the trig expression, which now you're seeing why all those identities and doing those proofs and stuff last semester in your trig class or last year in your trig class are like, ooh, that might actually come in handy. Here's an example of like, boy, that saved me a lot of hassle if I was actually pretty good at this. Violet.
You do 27 on
3.4, number 27? Sure. Again, that last problem there, Michael, is another example of like, when I talk about looking for a back door, that's kind of is a example of what I'm talking about, right? There's a algebraic way to make the calculus way easier. And if you see it, it's like there's a back door to this problem that just takes it from being like 10 lines and a bunch of crappy identities to like a real easy derivative rules. All right. So Violet, the way I see that square root in there, every time I see a square root, I really think about it as an exponent to the 1/2, right? So again, we'll have the bottom times the derivative of the top. Should be dr, and the bottom, the variable should match. And then minus the bottom times the derivative of the top, all over the bottom squared. So far, so good. So if I look, the squared cancels the square root. The derivative of r is just going to be 1. And then the derivative of r squared plus 1 to the 1/2, that's a chain rule. So I'm going to have the 1/2 inside to the negative 1/2. So we're going to have r squared plus 1 to the 1/2 minus r times, I'll just make it r over 2 times r squared plus 1 to the negative 1/2, all over r squared plus 1. Maybe I'll write that as like to the first. So far, so good. Now, this is not what the back of the book's answer probably looks like. So, again, calculus is done. As far as I'm concerned, you don't need to go any further. But if this is a multiple choice question, that's not going to be one of the answers. Almost assuredly, what they're going to do here is we're going to multiply the top and bottom by 2 r squared plus 1 to the 1/2. So when I multiply that to the first term, r squared plus 1 to the 1/2 times r squared plus 1 to the 1/2 is just r squared plus 1. And I still have that 2 out front, so that'll distribute through. So far, so good. The second one, the 2 will cancel, so I just have the r out front. And then r squared to the negative 1/2 times r squared to the positive 1/2 is just 1, right? It'll be r squared plus 1 to the 0, which is just going to be 1. And then I have r squared to the plus 1 to the first times r squared plus 1 to the 1/2. So that'll be r squared plus 1 to the 3/2. Oops. I would guess that the back of the book answer probably looks like that. Violet, does that feel okay? So like, again, the calculus piece, not too bad. How much do I need to simplify this? The answer is very little if it's just like a free response question on a Mr. Kulik test, or if it's a free response question on an AP exam, unless they're asking like, show that this is equal to this. Once the calculus is done, just stop. But if it's a multiple choice question, you got to be able to simplify to something that like, okay, I can see which one of these multiple choice answers should be the one I pick, which is sometimes tricky. So if I have a situation like this, my goal is usually just to kind of clear the fractions. Usually looking at the multiple choice options would give me a good idea of also where to go. When I see no radicals in the numerator, that would indicate to me I need to like multiply through by the radical that'll cancel them all out. But that's the gist of it. Does that feel good? Okay. What else? What else? Happy to do more if there's more questions or just general stuff. It could be super specific like we've been doing, or it could just be general. Either is okay with me. Paulo. Same section?
Yes.
Sure. Where did my mouse go? There. Okay. So I see function composition going on here, so I know I'm going to be using a chain rule here. What is the outer function for this? So if I'm talking about an outer function, it's like the x cubed, and the inner function is this quotient, right? You guys kind of see that? So if I do my chain rule, I'm going to have derivative of the outside. That look okay? The guts, the inside still stays the same. And then I have times the derivative of the inner. Now, what do I need to do the derivative of x squared plus 1 over x squared minus 1? Quotient rule. So I'll have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And the derivative of each of those two chunks is just 2x, right? So we're going to have y prime is 3x squared plus 1 over x squared minus 1 squared times, let's see, that'll be 2x cubed minus 2x minus 2x cubed minus 2x all over x squared minus 1 squared. So far, so good. Again, the calculus is kind of done in that previous step. I'm just kind of simplifying, right? So those guys can cancel, and I'm left with just minus 4x here. So if I collected this all together, I would have, say, minus 12x. That's the 4x times the 3. And then x squared plus 1 squared, or x squared plus 1 squared in the numerator. And in the bottom, x squared minus 1 to the 4th in the denominator. And that's probably the answer that's in the back of the book. That seems like a nice, neat answer to me. Would be what I'd be expecting from a multiple choice question. But again, like, You know, like if you have this where you have the two x's in there, if it's a free response question, you could stop at that stage. You don't need to like go crazy combining things. When the calculus is done, you can be done. The rest of this is just clean up algebra. You don't need to do that on a free response question, either for me or the AP, unless the directions are specific, like show that this thing is equal to this. But the place where you do need to be able to do the cleanup is in a multiple choice question to make sure you're getting, you know, that you can tell your answer and take it to whatever the options are. Does that feel okay? Last call on homework questions. I don't mind keeping going. It just felt like there was a little bit of a lull before Paula was like, I have one actually. Okie dokie. All right. Actually, this should be down here or something. Promote. Okay. So I want to do a little bit of bonus idea about doing derivatives involving inverse functions. So this is a little bit of a bonus thing. It's not explicitly covered in our textbook well, so I want to take a moment and talk about it because this is something that not uncommonly we'd see on an AP exam. So if you remember from your pre-calculus course and Algebra 2 course, the definition of inverses. So you have two ideas. So if f and g are inverses, we should really probably add in that, right? If I do the composition both ways, I get x. And that f of a gives me b, then g of b should give me a back, right? That g should undo everything that a did. So take a's output and return it back to its input. Everybody's okay with that idea? So let's say that I have the function then f of g is equal to x, right? If I take the derivative of both sides of this, well, the derivative of f composed g is just the chain rule. So it's the derivative of the outside times the derivative of the inside, and that'll equal 1. Everybody feel okay there? And if I divide now both sides by f prime of g of x, so the derivative of the outside, what I'm left with is like a formula for g prime. Does that feel okay there? Okay. So let's look at some example problems. So I've pulled these from previous AP kind of questions. Says that the functions f and g are differentiable for and then for all x, f of g of x is equal to x and g of f of x is equal to x, i.e. that's telling us that f and g are inverses, right? It says that if f of 3 is equal to 8 and g prime of 3 is equal to 9, what are the values of g of 8 and g prime of 8? Well, one of these is really simple, right? What's g of 8 have to be? It has to be 3, right? Because if I just take this and I go and do g of both sides, I know that g of f is, or g and f are inverses, so they just kind of cancel each other out. So like g of 8 is 3, right? Everybody feel good on that one? Now to get g prime of 8, I'm going to use that formula that I built from up above. So far, so good. Now, what's g of 8? That's 3, right? And what's f prime of 3? 9. It's given to me right here. So g prime of 8 must be 1/9. I feel pretty good. Okay, let's do another. Let f be the function defined by f of x equals yada, yada, yada. If g of x is equal to f inverse and g of 2 is equal to 1, what is the value of g prime of 2? Well, I know that 2 is equal to f of 1. Right, I can write that down right away. So I can also, using my formula, g prime of 2 is going to equal 1 over f prime of g of 2 So I know then that if g of 2 is equal to 1, I have 1 over f prime, right? Well, f prime, I can compute really easily because I have the formula for f. And it turns out I didn't need that at all, right? I just wrote it down because I knew I could. Didn't know if I was going to need it or not. Ended up not needing it. Does everybody feel good with that? Okay. Let f and g be functions that are differentiable everywhere. If g is the inverse function of f, and g of negative 2 is 5, and f prime of 5 is negative 1/2, what is g prime of negative 2? So we know that g of negative 2 is 5. That's given to me there. And I know f prime of 5 is negative 1/2. So 1 over negative 1/2 is just negative 2. So far, so good? Not too bad, right, Michael? Yeah, so I didn't have any, it didn't tell me what f prime of 1 is, but I did know f. So I computed f prime from f, and then I just plugged 1 into it.
So that's the derivative.
Right. Yep. So I just did the derivative of f, and then plugged 1 into it. So I just had to do it by hand. Whoop-de-doo-doo, right? Like I can take the derivative of a polynomial. Those are my favorite things to take the derivatives of because they are like the easiest. I love it. All right. So here we're given f and g are differentiable. And we're told a bunch of different values of the values of f, g, the derivatives of f, and the derivatives of g. So f of 1 is 2, f prime of 1 is 3, f prime of 2 is negative 4, g of 1 is 2, g prime of 1 is negative 3, and g prime of 2 is positive 5. Now, we probably won't need all this information to do what we're being asked, but they're giving us maybe more than we need to help confuse us, which the AP loves to do. That's okay. Let's figure out what we do need. So here we're told h of x is equal to f compose g. So h prime of x is going to be doing the derivative of both sides. So that's going to require the chain rule. And then if I do h prime of 1, so I'm going to have f prime of g of 1 times g prime of 1. Well, g of 1 I know, that's 2. G prime of 1 I know, that's negative 3. And then f prime of 2 I know, that's negative 4. So I get 12. What'd you guys think? No big deal, right? The key is just like using the chain rule or using that formula for the, the derivative of the inside if you have a inverse situation. Here on the last one, we didn't know that f and g were inverses, right? That's why I didn't use that formula we had developed before. We're just told they're differentiable, and we had the composition. So it's just a chain rule problem. What do you guys think on that? No big deal? Okay, just wanted to show it to you. Today, we're going to talk about implicit differentiation. So up until this point, we've only defined differentiation on functions that are expressed with a strict independent-dependent variable relationship, like y equals 5x plus 7, and not done things like y minus 5x equals 7. Right? So explicit is where it's written as one variable by itself. So everything is in terms of, like an independent-dependent variable relationship. An implicit equation is one where there's no independent-dependent variable implied by the way you've written it. So a canonical example of that is like the equation for a circle, x squared plus y squared is equal to 1, or r squared. Is everybody okay? So if we look at part A, it asks us to find dy dx. So I'm going to take the derivative with respect to x of both sides. Everybody's okay here? So what is the derivative with respect to x of x squared? 2x. What's the derivative with respect to x of y squared? Close. 2y dy dx. So what's really happening here, and okay, we'll explain this in a second. And then what's the derivative with respect to x of 25? 0, right? We'll come back and explain where this guy is coming from in just a second. Let's finish the problem up and then we'll talk about what's going on. All right, so now all I'm going to do is get that dy dx by itself. So I'll subtract the 2x over and then divide by 2y. So dy dx should be negative x over y. Everybody's okay there? Okay, so back to where this dy dx is coming from. So let's just say we had something like the equation y equals 5x squared. If I do the derivative of both sides, I'm going to do the derivative with respect to y. Derivative with respect to x of y, and the derivative with respect to x of 5x squared. Remember, one of the ways that we write a derivative of y is dy dx, right? So what's happening is the derivative of y is 1, and then we have this extra dy dx term. Just like over here, the derivative of 5x squared with respect to x is 10x, and then we really have a dx over dx term here. But what's dx over dx? Just 1, so we never really write it. This is the most common mistake and problem students have when doing implicit differentiation, is we forget to leave or to put in the dy dx's. Anytime you differentiate a variable that is a not with respect to the variable of differentiation, it creates a d whatever term. Everybody's okay with that? So if I did d dr of t, I'd get 1 dt dr. If I did d dz of x, I'd get 1 dx dz. If I do d dz of z squared, I just get 2z because the variable's matched. Is everybody okay with that? Okay. Let's finish this question up because there's a part B. So it says, then find the equation of the tangent line at the point 3, -4. So I know m is just dy dx evaluated when x is 3 and y is 4. So that's going to be -3/4. So I have y minus y1 equals m times x minus x1. And again, if you wanted to clean that up to put it into slope-intercept form, you're welcome to it, but that is good enough for me. Feel okay? So notice that this is a little bit different in calculating the derivative. I might need both x and y coordinates to plug in. That's okay. No big deal. Let's do another. So here we're asked to find y prime if x cubed plus y squared, or y cubed, is equal to 6xy. So what I'm doing, y prime is the same as dy dx, right? Everybody's okay with that? So I'm just going to be taking the derivative with respect to x of both sides. So what's the derivative with respect to x of 3x cubed? 3x squared. How about of 3y cubed? 3y squared dy dx. And then what's the derivative with respect to x of 6xy? What do you guys think? It's a product rule. Yes! We have two variable expressions, x and y, that are multiplied together. Have to use a product rule. Very good. Everybody feels so far so good? Okay. So notice the dy dx is in two different places, right? When that happens, I'm going to group the terms with the dy dx's onto one side and everything without a dy dx to the other side. So I'm going to subtract over the 6x dy dx, and then I'm going to subtract over the 3x squared. Everybody feel good here? Now, because the dy dx is in common with both terms, I can kind of factor that out. And then if I divide both sides by 3y squared minus 6x, I've got my dy dx all by itself. Does that feel okay to where I got?
So why is the dy dx there after 3y squared, like right under it? For the second one, how does it just get there?
This part?
Yeah.
So because I differentiated with respect to x, a variable that wasn't x. Anytime you do that, it's going to create a d, whatever the variable you're differentiating is, dx.
So it was like 3c, it would be dz over dx.
Yes. Everybody okay? Okay. You might notice that, hey, I can reduce that guy a little bit, right? Because everybody see a greatest common factor 3 in the top and bottom. Not necessary that you do that, but anytime it makes the numbers a little smaller, I'm in favor. All right. And then part B was find the tangent to the folium of Descartes, yada, 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 this thing. Apparently that thing has a name. It's a fancy name. At the point 3, 3. So I know m is going to be the derivative evaluated when x is 3 and y is 3. That all look good so far? Oh my goodness, Mr. Kulik, that's a 2. Yipes. That makes a heck of a lot more sense. All right, so I have 6 minus 9, that's negative 3. Over 9 minus 6, that's positive 3, so the slope is negative 1. So we have y minus y1 equals m times x minus x1. Look good there. And then part C says at what point in the first quadrant is the horizontal, or is the tangent line horizontal? So if I have a horizontal tangent, what's that telling me about the slope? So we just want to solve for dy dx equal to 0, right? So when is a fraction equal to 0? When the numerator is 0 and the denominator is not equal to 0. So far, so good? So this tells me then that y should equal x squared over 2, right? I'm going to take that back to my original equation. And I'm going to substitute that x squared over 2 in place of my y's so that I can now solve for x. So I'm going to have x to the cubed plus x to the 6th over 8 equals 3x to the 3rd. Is everybody okay there? Yeah, Michael?
Where'd you get the y equals x squared over 2?
So I just solved this equation for y. So I just got the y by itself. Is that okay? I'm going to go and get everything onto one side. So I have like 1/8 x to the 6th minus 2x cubed equal to 0. To solve that, I'm going to factor out a greatest common factor of x cubed. So far, so good. 1/8 x cubed minus 2. Does that look factorable to you guys? Looks a little bit like a difference of 2 cubes to me. Like 1/2 x cubed minus cube root 2 cubed. I know, you didn't see that right away, but maybe you did. That's not obvious. This is why we're doing it as an example. This is way harder than anything I'd ask you to do. The algebra here is pretty rough. Just hang on. I acknowledge this. So if I factor this, do you remember the difference of 2 cubes factoring pattern? I know. It's a minus b times a squared plus ab plus b squared. Here's the good news. What do you know about the roots to that polynomial? They are all imaginary. So if you do the sum or difference of 2 cubes factoring pattern, the trinomial piece of that is always going to give you imaginary solutions, which is good for us because we don't care about the imaginary solutions. I can just ignore it. Yes. So applying the zero product property, I just have x equals 0, and then x equals 3, or cube root of 2 over 2, right? Or I might be able to think about that as 2 to the negative 2/3 if you want. Doesn't really matter. So far, so good. I now just need to go back and check. Oh, maybe not yet. Okay. So now I need to get my y's. If x equals 0, I'm going to have 0 cubed plus y cubed equals 6 times 0 times y. What does y have to be? 0. So 0, 0 is one solution. And then if x is equal to, I'm going to write as negative 2/3 because that just like makes life a lot simpler. So I'm going to have 2 to the negative 2/3 cubed plus y cubed equals 6 times 2 to the negative 2/3 y. 2 to the negative 2/3 cubed is just 2 to the negative 2. And that I'm just going to leave the way it is. So to solve for y, I'm going to go ahead and get the y's all on one side. So I'm going to subtract the 6 times 2 to the negative 2/3 y over, and then subtract the 2 to the negative 2 over. I can factor greatest common factor of y here. Oops, no, I don't want to do that. What do I do here? The Yuckarooskies. Did I make a mistake? I need that to equal 0. Okay, no, I'm fine. So if I look at this polynomial, I have y to the y cubed, y to the first, and then a constant. Do we have any good method to factor that? No, you do not. No. Mr. Kulak, if I can't solve this by factoring, how would I be solving this? Starts with a G and it ends in a G. I'm going to do it by graphing. I'm just going to plot that polynomial on my calculator and find its x-intercepts. Assuming that I haven't made any stupid typos. You know what I mean, guys? All right, let's get that out of there. So I know it says y, but I'm just going to use x's. Oops, 2/3. And then I'm going to just graph this on the standard negative 10 to 10 window. So there's one solution there. Oh, yes. Did I? Thank you. Yeah, I sure as heck did. I was like, I was expecting 2 solutions out of that. Thank you. Oops. All right, try it again. Okay. So I have 3 solutions here. So I have here at negative 2 something. I have here again at 1 point something, another over here. So negative 2.2. And then we have 0.44. This is more than I thought I was going to get. Makes me suspicious here. Trace 0. and 1.68. And I want to take a quick peek at this. Yeah. Yes. Ah! I found it. That's infuriating. Take a look. See if you see it. So I added root 3 over 2, and then I should have multiplied by 2. What did I write, though? Divide. Ugh! Okay. All right, let's try that one more time. Yes. What happened here? All right. You know what? I'm moving on. There's some little stupid mistake in there somewhere, but you guys at this point got the gist of it, right? It was a long time. Let's do the next one. That's not nearly so awful. Sure. All right. So we want to find y prime for sine of x plus y equals y squared cosine x. So we're going to be doing the derivative with respect to x of both sides. What do I need to do the derivative of sine x plus y? Chain rule. So the derivative of the outside is cosine, and then the insides. And the derivative of the inside, what's the derivative of x plus y? 1 plus dy dx. Everybody feel okay there? What do I need to do the derivative of y squared cosine x? Product property. So derivative of cosine x is negative sine x. And then the derivative of y squared is 2y dy dx, right? So far, so good. Now we're just going to have a bunch of yucky algebra here. So let's simplify things down a little bit. So I'll distribute my cosine x plus y through. And then we'll multiply our stuff together. Does everybody feel okay to there? I'm going to put my dy dx on one side, everything else on the other. So I'll subtract the 2y cosine of x dy dx onto this side, and I'll subtract the cosine x plus y to the other side. And then I'll divide both sides by cosine x plus y minus 2y cosine x. And we are at the finish line.
Would you make us simplify even from there?
No way, dude. I'm not even sure there's anything more to do. Without busting out like a sum or difference identity for the cosines, I don't think there's anything you can do. And even there, I don't know that you're going to get anything to nicely simplify down. I think that's just going to be what it is. What's different about this next one? It's asking for the second derivative. Oh no! So we'll start with the first derivative. Okay. Derivative of x to the fourth is 4x cubed. The derivative of y to the fourth, 4y cubed dy dx. And the derivative of 16 is 0. Everybody's okay? So we have a couple of options here. I can get the dy dx by itself and then do my derivative. Or I can leave it the way it is and just do my derivative here. I usually like to do the second option. It tends to be like less algebra. But there's a little thing we have to be careful about if we go this route. What's the derivative of 4x cubed? 12x squared. What's the derivative of 4y cubed dy dx? Product rule. again, would not have guessed that there, but now that you say it, I see it. So what's the derivative of dy dx? It's d squared y dx squared, aka the second derivative. What's the derivative of 4y cubed? 12y squared dy dx. Okay, so this is the thing I need to get by itself, right? Everybody see that? So I'm going to subtract over the $12x squared, and I'm going to subtract over the 12y squared. What's dy dx times dy dx? Dy dx squared. And then we'll divide both sides by 4y cubed. And then my last step here is going to be substituting in for dy dx, which I guess I did need at this step. So let's reduce out the four. There I have that. And the rest of this is just algebra cleanup from here. That got kind of nasty. Those second derivatives can be rough, boys. Okay. Sure. The last piece here is that I'm going to introduce for you guys some more derivative shortcuts. So we have derivatives for anything that's written as a power function, like x to the n. We have e to the x. We have all of the trigs, sine, cosine, tangent, secant, cosecant, cotangent. We have a to the x. Now we're going to have the inverse trigs. So sine inverse, cosine inverse, tan inverse, etc. So I've got them all here collected together. But let's do this last example here. So I have y equals 1 over sine inverse of x. As it's currently written, what would I need to use to differentiate this? Quotient rule. That stinks though, right? Alternatively, the way I would think about this would be thinking about sine inverse to the -1. If I do it this way, I can think about it as we chain rule, that seems preferable to me. So derivative of the outside times the derivative of the inside. And I know from my table, the derivative of sine inverse is 1 over square root 1 minus x squared. That can be my final answer. Mr. Kulik, do I need to memorize these guys?
Yes.
Yes. Yes, you do.
Yeah. For the chain rule. So for the first part, it's F, G, F, G prime of x, right?
F prime g of x.
So
It's the derivative of the outside with the guts staying the same.
pretty much on the outside, it's just x to the x.
Yes. And then this is the homeworks for this one. This is a tough boy homework. Just as a warning, we'll plan on lots of questions on Monday when I see you again, but we won't talk about it on Thursday. Why not? Test corrections are Thursday. The test corrections are Thursday.